Hey everyone, welcome back to my channel. In today's tutorial, I'm going to demonstrate how to produce correlation matrix and interpret correlation matrix in Stata. So in order to do that, I have already loaded my data in Stata interface. So what I do now is to talk about correlation coefficients or correlation matrix. So what is correlation? So correlation actually measures the linear relationship between two variables. Okay, so how they are related? They look at the direction of the relationship and also the strength of the relationship. So what is the direction of the relationship? Direction of the relationship is whether the direction is positive or negative. For example, if income goes up, so with the higher level of incomes, quality of life also goes up, right? So income is positively related with quality of life, right? But uh, the relationship could be negative as well. For example, if education levels go up, uh, so your conservative attitudes go down. Okay, so education level now related to negatively related to conservative attitudes. Okay, so relationship could be negative, relationship could be positive. And now, what is the strength of the relationship between two variables? The strength is how strongly they are related. So income is related to higher quality of life, but how strong that relationship is. So we look at the strength of the relationship at certain numbers, or what we call coefficients in case of correlation, right? So we look at correlation coefficient, we look at the direction, and now whether that strong correlation is statistically significant or not, we can produce p-values for them, right? So we look at the strength, we look at the direction, and we look at statistical significance of the relationship of two variables. Okay, so that is in a nutshell a correlation. So first, you need to make sure that all your variables that you are working on, are stored as a numeric variable. Okay, not as a text data or string variable. If that is string, you cannot produce any results for correlation matrix. So I'm gonna use some of the variables that I have been working on. Let's copy this from my do file and put it here. So I'm going to check whether they are numeric or string. So I'm going to write describe command that I have shown you before and hit enter. Describe, this is misspelled, describe. Okay, so what you see in integer, byte, float, so and the display format, none of this is a string, all these are numeric. Okay, so therefore this confirms that we can proceed with the correlation matrix of these variables. Okay, however, one thing you need to be mindful of is there are three variables. For example, diabetes, female, black, they are measured as a binary variable. So for example, female coded as 1 equals female, 0 equals male, black 1 equals black, and 0 equals non-black or not black. Diabetes 1 equals diabetes, no diabetes or non-diabetes is 0. Okay, so just one unit change, 0 to 1. So that is 1 means 1 unit in this case. Okay, so now let me copy this again here. These variables are in these variable windows. Okay, I have copied this from my do file in order to make it easy. So I'm going to write a command pwcorr. So let me explain this code for you. PW means pairwise, core means correlation. So in short, this data language for correlation coefficient, the code is PW core, pairwise correlation. Okay, And then I'm going to add an option sig, which is significance. I'm asking for p values for the relationship, and hit enter. So now let me explain this table for you. I'm not going to explain each one of them, but few of them, so that you can get an idea of how these are interpreted. Okay. So now look at BP systole and BP systole. Okay, the relationship between two. This is called coefficient. The first number is called coefficient. The first number called correlation coefficient. Okay, the second number is the significance level. Okay, the p-value, and you know that the p-value, any value that is less than 0.05, is statistically significant, right? So you can see these values are less than 0.05. All these are significant. But why don't we have the significance level for this? Because this is perfectly correlated. Perfectly correlated. Why? Because they're the same thing. Okay? BP systole and BP systole. So now the question becomes, what is the range of correlation? So correlation ranges from -1 to +1. Okay? -1 to +1. So any values that are close to +1 is considered a strong positive correlation. And any values that are close to -1 are considered a strong negative correlation. So we can see the direction, right? So this is the -1, but this is positive, okay? +1. And now we need to understand the direction, which is negative or positive, and then strength. So how do you know about the strength? Okay, now let's look at age and BP systole. So what do you see here? You can see that this relationship is statistically significant, and we have correlation coefficient of 0.48. Okay. Now I'm going to give you a rough estimation of weak, moderate, and strong correlation. When do you define two variables are weakly correlated, or moderately correlated, or strongly correlated? Okay. So the rule of thumb is 0.1 to 0.3 will be considered in both direction, negative or positive, will be considered weak correlation, and 0.3 to 0.5 moderate correlation, and 0.5 to 1 both direction is considered a strong correlation. So what do you see here? You have correlation coefficient 0.48, right? So that is close to 0.5. So we can roughly consider this as a strong correlation, because, and how do you interpret them? And this is also statistically significant. So BP systole is systolic blood pressure. So we know that the increase in age, meaning that people grow older, have higher levels of BP systole. So BP systole also increases. As age increases, BP systole is also increases, or age is associated with an increase of BP systole, or systolic blood pressure, right? So which makes sense, because the older people have higher probability of experiencing systolic blood pressure, right? So now, one important note here: you cannot explain this relationship from the correlation matrix as the causal relationship, meaning that one variable causes the other variable. That's not the case. Okay, that may not necessarily be the case from the correlation matrix. It could be the case with some more advanced level of screening. That's a discussion for another day. But from the correlation matrix, you cannot determine if the correlation between the two are causal. They could be causal, but not necessarily, right? Okay. So, but from the correlation matrix, we can see that how variable move together. So as age increases, BP systole also increases. That's what we see, and that is a strongly correlated and statistically significantly correlated. Okay. Yes. And then let's go to female. So as I mentioned that this is binary variable, and binary variables correlation with the another variable needs to be interpreted cautiously. This is not the same as the continuous variable. So how do you interpret binary variable? So female here means female is equal 1 and male equals 0. So we can see the negative sign, and we can see the correlation coefficient, and we can see that this is less than 0.05. So now let me interpret this to you. So the interpretation it would be that the relationship between female and BP systole is negative. So that is the direction. And now the strength. So as I mentioned, that zero point 0.1 to 0.3 is weak correlation. So even it is less than 0.1, so that is even weaker. So then the weak. Okay, so this is not strongly correlated or moderately correlated or even less than weakly correlated, right? So this is basically, we interpret this weak correlation, even though we see this they are statistically significant. Okay, so we interpreted direction, we interpreted strength, we interpreted statistical significance. But for the binary variable, the way we interpret is that there are two groups, like male and female. So we interpret the group means difference. Group means difference. Okay. So the mean difference between male and female for BP systole, the score is statistically significant. Okay. And meaning that female have or female tend to more likely have lower average BP systole or systolic blood pressure compared to male. Okay, so here we are comparing two groups in this binary, correlation coefficient. But we discard this as an important correlation because this correlation coefficient is very weak. Okay, and I think this has been interpreted. Now, one more thing. So, what if your correlation is really too high, like 0.9 or 0.85, 0.95, in both direction, negative or positive? What if that is the case? So when you really have very high correlation coefficient, that means you will have a trouble actually if you go for the advanced statistical analysis like regression. What trouble we have? The trouble is that you'll face multicollinearity, one of the violating metric of regression assumptions. Okay, so you violate the regression assumption with a high multicollinearity score. So how that happens? That happens because two variables really have high correlation, meaning that the assumption is that they need to be really independent of one another. Like they're measuring two different things. But when you see a high correlation coefficient, that means they are kind of similar thing, right? As you see, these are perfectly correlated. But when you have two variables that are even not perfectly correlated, but close to one, right? Like 0.9, 0.85, this really is a problem because they might be measuring the same thing. They are not conceptually and empirically different from one another. But the assumption in the regression model is that they need to be independent of one another. Okay? So therefore, if you really have a too strong relationship between two variables, that's a major sign that you will have trouble. But that's not necessarily the case unless you test it for like what it's called VIF, variance inflation factor, which we'll talk about later. But for now, you need an idea that too strong correlationship is not what we want. Okay, so what we want is moderate to strong, but not too strong. Okay, and now let me produce this correlation metric in a graph. So, like in a scatter plot. Okay, let me get my do file where I put my code because it's not always on top of my head. So yeah, I'll copy it. You can run it from here, but I'll copy it to my command window. And if you use graph and metrics, because it is a correlation matrix. So, and another important thing in visualization, you cannot use the binary variables. Okay. So graph metrics and the name of the variables, pretty simple, and then hit enter. and you'll get this correlation matrix, like this one, body mass index and systolic blood pressure, and how they are related. As you can see, the body mass index goes up, and also systolic blood pressure goes up. So you can see this pattern here. Okay, but you can use half to make it better visual. So half as an option, so it brings you only the half of it. So it's better visually, better to me. But mm, you can make your own choice. Okay. So that's it. Thanks for watching. If you really like my videos, please subscribe my channel and like, comment, and share. Also, if you want a specific video to be created, let me know. I will create a video for you. Thanks again.